Okay. Let me open it up. Let's see what we got here.
I have one more coming for you.
Okay, I didn't get that one yet. You sending it to David Cowan 1949 at Gmail?
Yes, sir.
Okay. You know, there it is. I was going to say, it took a long time for your audio to come on.
Yeah, it did.
Kind of come to the conclusion that that is a measurement of one's internet speed at that particular time.
Really?
I think so. Yeah, I do. And so you guys use Comcast or CenturyLink?
Comcast, I believe.
Okay. Yeah, I don't know why the internet speed would vary. Comcast's generally pretty fast. They're really fast in my area. A lot of that has to do with whatever box they have in your area. They may not have, you know, same speed where you're at as where I am.
Yeah.
All right. So which one do we want to start on here?
So I figured out the first two with a little bit of help from a friend. So I was thinking 3, 4, 5, and 6.
Okay.
And then number 9. I think you should be able to see that one. And then I also sent you another picture with, I think it was numbers 11 through 13 and 17.
All right. Well, let's start on 3.
Alrighty.
How many different ways can 5 students sit in 5 chairs in a row? Well, let's forget this exception for the moment. How many ways could 5 students sit in 5 chairs? Let's take chair A. How many different ways can students sit in chair A?
120?
No, 5. There's only 5 students. There's only 1 chair.
It says 5 chairs though.
Right. So here's what we have. Here's the picture we have. We have chair A. We have chair B. We have chair C. We have chair D. And we have chair E. There's 5 students to sit in these 5 chairs. How many different ways can somebody sit in chair A?
5.
There's only 5 students. 5. With me?
Yep.
Now, once a student is sitting in chair A, how many ways are there for the other 4 students to sit in chair B?
4.
And so on and so forth. So that would be the answer if we did not have this exception.
Yeah, it would.
So now we got to figure out what that means. If 2 of the students refuse to sit next to each other, wow. Well, we'd still have 5 ways, right? For the first chair. And in the second chair, sometimes there's 4 ways. Sometimes there's only going to be 3 ways. Because Mark may be sitting in chair A, and Ophelia would be one of the 4 other people. So those are, it's not going to be 5 times 4 times 3 times 2 times 1. Question is, the question is, how's it going to be? Yeah, because this combination would occasionally result and Mark and Ophelia sitting next to each other. Let's talk about that for a second. Because if we can figure out how many ways that would happen, what is this? That's 20 times 6. That's 120 ways that they'd be able to sit in 5 chairs without that restriction.
Mm-hmm.
Now, how do we talk about that restriction? For Mark and Ophelia not to sit next to one another, I think it's going to be 5 choose 2, which is 5 factorial over 3 factorial times 2 factorial, which is 5 times 4 over 2. There appear to be, if I'm correct, 10 ways for Mark and Ophelia to sit next to one another.
Okay.
Let's talk about that for a moment.
But that's not the actual answer, right?
Oh, hold on, we're just getting there.
Okay.
This is still seat A, seat B, seat C, seat D, seat E. Well,
yes.
If Mark sits there, Ophelia could only sit in 3 seats. So she would have to sit either there, or there.
Yeah.
So there are 3 ways if Mark sits in the first seat. If Mark is sitting in the second seat,
There's 2 ways.
yeah, because she couldn't sit there, she couldn't sit there, she'd only be able to sit there.
Mm-hmm.
If Mark sits in the third seat, there's 2 ways. If Mark sits in the fourth seat, there are 2 ways. And if Mark sits in the fifth seat, there are 3 ways. So it looks to me like there's 12 ways. That's not the way to do this. That's 12 ways for them not to sit together. Let's do the same exact thing, only let's change it slightly. I know there's 120 ways for these 5 kids to sit. Let's figure out how many ways Mark can sit next to Ophelia and subtract those from 120. Well, if Mark is sitting in the A seat, there's only one way for Ophelia to sit next to him. She'd have to be in the B seat.
Mm-hmm.
Mark sits in the second seat. There's 2 ways Ophelia could be next to him.
Yeah.
Same in the C seat, same in the D seat. In the E seat, there's only one way. So there's only 8 ways for them to sit next to one another.
Yeah.
The reason this didn't come out to be 10, or the reason I came out with 8 instead of 10, is that this would technically count if they were sitting in the end seats, they would be next to one another.
Yeah.
And that's not true. In other words, I specifically came up with 8 ways that Mark and Ophelia could sit next together, and only 8.
Yeah.
So if they're not going to sit there next to one another, then we have a total of 112.
Yeah.
That should be the answer. Do you have answers on these?
Yeah. I have the answers, and apparently, according to the back of the book, the answer was 72.
You're kidding.
The only thing I can think of would be that it is 4 times 3 times 3 times 2 times 1. Because I mean that's 72. That's the only combination I'm seeing.
Huh. Trying to figure out why my method did not give me the right answer. I guess No, I covered all combinations. In other words, regardless of which seat Mark is, Mark can only be in one of these 5 seats. And if he's in the middle 3, there's 2 ways for Ophelia to be next to him. And if he's in the end seat, there's only 1 way. So it definitely seems like it's 8. And it doesn't matter the order they're sitting in. You could put Ophelia and Mark in any order next to one another, and it's going to be one of these 8 ways.
Oh, yeah.
Whether it's Ophelia there and Mark there, well, if Mark is in the D seat, Ophelia can either be in C or E, so that's 2. So I'm pretty sure there's only 8 ways. Out of 120. So how did they get 72 as an answer?
I do not know, honestly. Sorry.
No, I hate these probability problems. They're not really probability problems. They're combinatorial or permutation problems.
Mm-hmm.
They're very difficult for me. You know, we all have our strong suits in math.
Yeah.
We all have our weak suits. And one of my weak suits is combinations and permutations. I know a little bit about it, but solving problems is hard for me to do.
Yeah.
So let's just go on. 4,
okay.
I can do.
You know how to do 4?
I know how to do 4.
Well, good. Let's get her done, because I honestly, I have not understood these for a long time.
Well,
I don't get these.
Simple step that you have to take to do these. And that step is figuring out how much you can do in a unit time frame. In 1 hour, how many jobs can Tristan do?
Oh fudge. I don't.
She can do 12 jobs in 15 hours. How many jobs can she do in 1 hour?
I do not know.
12 divided by 15.
So 3/4 of a job.
Yeah, that's 4/5. 3 goes into the top 4 times, 3 goes into the bottom 5 times.
Wait, would that be a rate instead of the time?
Well, that is the number of jobs she can do per hour. 4/5 of a job.
Mm-hmm.
Okay? That's all you need to know for the moment, is what Tristan can do all by herself in terms of a per hour. Okay? When Isolde helps him, they do 25 jobs in 20 hours. So together, they're doing 25 jobs in 20 hours, or 1 1/4 job per hour.
Or 5 jobs in 4 hours?
You want to get it down to an hourly basis. And you'll see why in one more step. I don't want to say 5 jobs in 4 hours. I want to get it, how many jobs can Tristan do per hour, and how many jobs can Tristan and Isolde do per hour?
Yeah.
Well, if Tristan can do 4/5 of a job all by herself, and working together they can do 5/4 of a job, then how much is Isolde doing? It's 1 1/4 minus 4/5. That's how.
Really?
Yeah. In other words, this is what they're doing per hour working together. This is what Tristan does per hour working alone. So
yeah,
the difference between these two numbers has to be what Isolde is doing. So what is that? If we have a common denominator, and I got 5/4 minus 4/5, 20, so I got 25/20 minus 16/20, 9/20. That's how much Isolde, how long it takes her. That's how much job she can do per hour. How many hours does it take her to do one job? If she's doing 9/20 of a job per hour, how many jobs can she do, or how long does it take her to do a full job? It's the reciprocal.
9/20
It's the reciprocal of that number.
to 29.
And think about that. That fits. She's doing almost a half a job per hour.
Yeah.
So she can do about two jobs per, or 2 hours to do a job. Well, that's almost 2. It's a little bit more than 2.
Yes.
So it's really 2 2/9 hours to do one job. And the secret to this problem is to figure out what each person can do in 1 hour. It doesn't have to be hours. If these were in minutes, say, if everything was in minutes, then I'm going to figure out how many jobs she can do in 1 minute. I want a unit time interval work expectancy. Once I have that, then I can combine everybody. Because when they work together, think about painting a house, okay? You start painting a house in one corner.
Yes.
And you can paint the entire house in 4 hours.
Yeah.
I'm slower. Takes me 6 hours to paint the whole house.
Yeah.
Okay, well, let's go through that one, because that one's actually a great illustration of this problem. So, David, I can paint the house in 6 hours, and Justin can paint the house in 4 hours. What part of the house can I do per hour?
1/6.
What part do you do per 1 hour?
1/4.
Now, if we're working together, and you start in one corner and I start in the other corner, we're just as efficient, right?
Yeah.
Okay, well, at the end of 1 hour, you will have painted 1/6 of the house, 1/4 of the house. I will have painted 1/6 of the house. Together, we've painted this much of the house. That's 3/12 and 2/12. Together, we've painted 5/12 of the house working together.
Yeah.
So how long would it take both of us to paint the whole house working together?
12/5.
Yeah, that's the way you do these problems. Just always break it down to what part of the job you can do per unit time measurement.
Okay.
And most of these are hours. This one's hours. Could be, like I said, minutes. Could be days. You know, if we're talking about painting a house, it might be days. So it doesn't matter. But whatever it is, whatever the time frame is, figure out how much of the job each individual can do in 1 hour.
Okay.
Okay, and that is the secret entirely on doing those. And then once you come up with the answer, in other words, working together, we can do 5/12 of the house.
Yeah.
Well, again, it's relatively easy to see that if you flip that, you get the total amount of hours it would take. If this came out to be 1/2, then clearly it would take us 2 hours to do the house. So using the reciprocal to figure out how many hours it's going to take working together makes a lot of sense also.
Yes.
All right. those used to give me horrible problems. They're called work problems, not word problems, but work problems.
Yeah, exactly.
They actually have a rate. I mean, they have a formula, which is 1 over one person's rate plus 1 over a different person's rate equals 1 over the total time.
Mm-hmm.
The problem is this formula is kind of hard to understand and apply. And
Yeah.
I have always found it to be much, much easier to do it the way I've described to you. Figure out what they could do in 1 hour, and then you can always combine them as necessary.
Huh.
Number 5, how should this equation read?
So can I tell you how I started it, and then we try to see if we can move from there?
Yeah.
So I started it with the equation x equals y squared over z times the square root of w.
Okay, there's only one thing you're missing, and that's a k. There's always a constant. Now, in these kind of problems like this, we don't need that k. It's not going to affect anything. But I'm a little nervous leaving it out, because a lot of problems which are varying problems, whether it's varying directly or inversely or jointly, they're going to require that k. So you should get used to writing it in there. So really what it is k y squared inversely with z and inversely with the square root of w. So there's
I was just missing a k on the top.
What's that?
I was just missing a k on the top.
Exactly. And notice for this problem, that k is immaterial. I don't need it, because I can figure out that what happens to x when y is multiplied by 3? What happens to x?
When y is multiplied by 3, well, it goes up.
By a factor of what?
3.
Y is being squared.
Oh, a factor of 9?
Exactly. In other words, what if y were 1? Okay? X is going to be whatever it's going to be. Now, multiply y by 3, so it's now 3, but I got to square it, so it becomes 9. So x has to go up by a factor of 9.
Okay. How would I write that part of the equation then?
Well, first of all, they want a net answer. They don't want what happens to x as y is multiplied by 3. They want to know what happens to x if y is multiplied by 3, z is doubled, and w is quadrupled. So let's write that. Y is multiplied by 3. Z is doubled.
So 2z.
And w is quadrupled. What does square root of w quadrupled equal?
Square root w squared.
So, now, we know that x is going to go up by a factor of 9, given the fact that y was tripled. So, up by 9. But then it's going to go down by half, because w was doubled. Excuse me, z was doubled. You with me?
Yeah.
And then it's going to go down by the 4th root of this. In other words,
4? Well,
let's just plug in a number. Sometimes that's the best way to do it. If w is 4, then square root of w is 2, right?
Yes.
And I'm dividing by the square root of w. So normally when w is 4, I'm dividing by 2 to get my answer x. Well, now W is quadrupled. Well, 4 times 4 is 16. So now I'm taking the square root of 16, which is 4. That makes us divide by 4 instead of 2. So x goes down by another factor of 2. So x should go up by 9/4. Check that and see if that's correct.
Yes, sir, it is right.
All right. And k never came into play. But a typical problem involving direct variation is you need the k. And in fact, they'll give you a z, a y, and a w, and your first step is to solve for k. And once you solve for k, you have the specific equation that governs this particular problem. And then they'll say, okay, now that you solve for k, tell me what x is when y, z, and w are different numbers. So in a problem like that, you would need the k, and that would be the first thing you would do is solve for k.
Yeah.
But in this problem, they merely want to know what effect all of these changes on y, z, and w are going to have on x. K doesn't do anything. K is the same regardless, so I could take it out. And
So we don't necessarily need k.
well, you don't need k in this kind of a problem. But
It's not normally we would need it, but not in this one.
Yes, and by normally I mean 90% of the time. These are kind of unusual problems. I would say that 90% of my students that work with problems that begin if x varies, the first thing you got to do is solve for k. And k is always in the numerator, regardless of whether it's direct or inverse or joint variation. K is in the numerator. But the real trick here is substituting 3y for y, substituting 2z for z, and substituting w squared for the square root of w. And then figuring out what numbers that produces. And the w squared was the hardest one for me to see. And the way I figured it out was by just picking a number for w, like 4.
Yes.
That would have meant dividing by 2, and if I increase w by quadrupling it, it becomes 16. Square root of 16 is 4. So now I'd be dividing by 4 instead of dividing by 2. So when I quadruple w, I only decrease x by half. And that's where that other 2 came from. The first 2 came from doubling z. Clearly, when I double z, I cut x in half.
Yeah.
Same thing happens when I quadruple w.
Gotcha.
All right.
Got 6 and 9.
Okay. On these rectangle problems, always draw a picture. The length, width, and height of a rectangular box. Hold on. Not particularly good at drawing three-dimensional objects, but I am getting a little better. There's our rectangular box. We'll call this the height. This will be the width, and that'll be the length. How about that?
Awesome.
Okay. The first sentence. Give me an equation that I can write.
L plus W plus H equals 150.
Okay. The length is twice the sum of the width and the height. Give me an equation I can write for that.
L equals 2 times, and then in parentheses, W plus H.
And the length is also twice the width is 1. Oh, hold on. No, this is completely separate. Twice the width is 1 centimeter greater than the height.
Yes.
Give me that equation.
Twice the width is 1 centimeter greater than the height.
Give me that as an equation.
2W equals H plus 1.
H minus 1. The width is 1 centimeter greater, no, twice the width is 1 centimeter greater than the height. It is a plus, my mistake. Okay? Now, notice what I have. I have 3 equations and 3 unknowns.
Yeah.
They're not even hard to solve. Normally 3 equations and 3 unknowns are hard to solve. But notice that I can do a lot of substitution here. I can solve these by substitution. So I'm going to go to equation number 1. And wherever I find L, I'm going to substitute that. So I got 2W plus 2H. That's my L. Plus W plus H equals 150. Now I'm going to go down to this third equation, and W is H plus 1 over 2, right?
Yes.
So I'm going to go back to this equation that I have right now, and wherever I find W, I'm going to put H plus 1 over 2. Well, this term becomes H plus 1. This is still 2H. This becomes H plus 1 over 2, and this becomes H. Now notice that I got one equation and only one variable.
Yes.
I can solve for H really easily. You know how to solve for H there? Do we need to go through it?
Wait, but I have...
Let's solve for H, and then we'll go back and solve for W using this equation. Once I solve for H, I'm going to be able to solve for W.
Okay.
And once I solve for H and W, I'm going to be able to solve for L. So
Yes.
just like any time you have 3 equations and 3 unknowns, your first goal is to solve for one of the unknowns, and then work your way backwards to solve for the other 2. It's the first step in solving this equation right here. Now we get rid of all denominators and parentheses. That's always a good place to start in solving equations.
Yes.
The way I'm going to do that is I'm going to multiply every term I see by 2.
Okay.
That gives me 2H plus 2 plus 4H plus H plus 1, so all I lose is the denominator there, plus 2H equals 360. Now,
why did we multiply them by 4?
I didn't. I multiplied everything by 2.
Well, why did we do that?
To get rid of this denominator of 2.
Oh, dude, I get it. Okay.
Okay? In other words, there's only one way to solve this. Well, there's a couple of ways to solve this equation. I can invoke a least common denominator and use fractions and solve it. But everybody hates fractions. So the sooner you can get rid of fractions in an equation, the better off you're going to be. And it's all I got to do to get rid of this 2 is to multiply both sides of the equation by 2. So that's what I did. And now it's really easy. I got 2H, 4H, Another h, that's 7h, and 2 more h, so I got 9 h's. I got a plus 2 there and a plus 1 there. That's plus 3. That has to go over to the other side. So the other side becomes 357. H is equal to 357 divided by 9. Now, is 357 divisible by 9? I don't think so. Let's see. Those digits add up to 6. You know that little test? That's a nice little test to know. Whether or not a number is divisible by 9.
It is not.
Add up the digits. And by adding them up, I mean 3 plus 5 is 8, plus 7 is 15, and then I got to add the 1 and the 5 to come up with 6. So the digits add to 6, which does mean it's divisible by 3. So I can simplify it a little bit. If I divide the top by 3, I get 119. If I divide the bottom by 3, I get 3. 119 is definitely prime. So that's a final answer for H. Now, you're going to use this problem to solve for W, because I know H now, right? W is H plus 1 over 2. And then we're going to, once we've solved for W, in other words, once we've solved for H, but after we solve for W, now I'm going to go back to equation 1, and that will allow me to solve for L, because I will know what W and H are. And then I'll have my 3 dimensions. Now, the only thing I'm not liking here is the fact that we didn't come up with an integer. And that's a little problematic because these equations are complicated enough that if H is this fraction, God, now I got to do H plus 1 over 2. That's probably going to be another fraction. 122 divided by 6, yeah, that's not divisible by what I'm going to have. So that's going to be a fraction. So I'm going to have a fraction for H. I'm going to end up with a fraction for W, which most likely means L will be a fraction also. So it's not hard arithmetic from this point. And I would suggest we go on just because I don't like spending my time doing arithmetic. I don't think you learn anything, and I don't. In other words, you're either going to be able to do it manually on paper or you're going to do it in a calculator. So
manually.
Well, okay, but regardless, we're going to assume you know how to do that. You wouldn't be taking this level math if you didn't know how to figure out what W was. Correct? So I'm going to test you. Tell me what W is.
W is H plus 1 over 2.
Do it step by step. But H is 119 over 3.
Plus 1.
Plus 1, all divided by 2. Now, how do I do that? How do I come up with that value?
That would be 122 thirds.
Okay.
Divided by 2.
So that's 122 sixths.
Yes.
And that is what W is. And that's also a fraction. In other words, 122 is not divisible evenly by 6. That answer is 20 and a third. Okay. Well, that's kind of good. Let's see. This goes in there. That's a remainder of 2/3. That's a third. That tells us L is going to be a whole number. Right? In other words, H, if I got my answers pretty close, I'm going to write up here in the upper left. L plus W, which is 122 sixths, plus H, which is 119 thirds. Well, 122 sixths is 20 and a third, and 119 thirds, ooh, I didn't, yeah, no, that's right. 119 thirds is 39 and a third.
Mm-hmm.
No, L is going to be a third. L is going to have a third with it. You see why?
Yeah.
And in fact, what do these total? These total 59 and 2/3. And so L has to be 90 and 1/3. 59 and 2/3 plus 90 and 1/3 add to 150.
I got W equals 61 thirds, and then
Correct? That's what
the
I
length,
got. That's what I got.
and then the length equals 244 thirds. Because I'm multiplying, adding 122/6 plus 61 thirds, multiplying that by 2.
Now, hold on. You're duplicate. 122/6 is 61 thirds.
Oh, yeah.
That's where you got your 61 thirds from. So I'm really adding 61 thirds and 119 thirds.
Yeah.
Which is 180 thirds. And 500 is 1,500 thirds. So I got 1,500 thirds minus 180 thirds gives me 1,320 thirds. And that should be L. Do they give you the answers in thirds, or do they give them to you as proper fractions?
119 thirds plus that. Well, 2 times 119 thirds plus 61 thirds.
Where are you getting 2 times 119 thirds? 119 thirds is what we got for H. So
Yeah.
if I label my box up here,
I took, well, because the length is 2 times the width plus the height. So it's 2 times, in parentheses, 61 thirds plus 119 thirds. And I just did that in my calculator, and I came up with 120.
well, what is 119 thirds plus 61 thirds?
180 thirds.
Which is exactly 60, huh?
Yeah.
So the length is 120.
Yeah.
Okay. Yeah, so the length was a whole number. I'm not sure what I did wrong up here to think the length, I ended up getting a third with the length, but I can see your logic. The only difference between us is I used that equation to solve for L. You used this equation to solve for L.
Mm-hmm.
And actually, this was the easier one to use, the one you used, because I got to do subtraction. I got to get rid of the W and the H up there, whereas this one's already solved for L if you know W and H.
Mm-hmm. Yeah.
Ah, okay. W and H, that is 180 over 3, which is 60. So L has to be 90. Excuse me. Yeah, L has to be 90. Twice.
2 times 60.
That's 120. Well, now the whole thing doesn't add to 150. The sum doesn't.
Huh.
What's wrong here? If W and H is 60, then L should be 120. L is twice the sum of the width and height. And twice the width is 1 centimeter greater than the height, which is that third equation. Well, I don't see our problem. It doesn't fit, you see. In other words, if W and H are 60, then L's got to be 90.
Yeah, you're right.
Not 120. Because L plus W plus H have to add to 150. So if W plus H is 60, the remainder has to be 90. So
Yep.
I'm not sure. These almost seem like they're contradicting one another, or else we've made a math error somewhere along the way. And we didn't come up with the proper H. There's a lot of arithmetic we had to do here.
Yeah.
So it's real easy to make a math error, and certainly not worth our time to go back and find it. As long as you see the way we're doing it. In other words, we wrote 3 equations and 3 unknowns. And then it's just a question of solving that system of equations.
Okay.
And they made it particularly easy to do because the equations they gave us, well, one was solved for L, and the other was solved for 2W. So they made it relatively easy to solve this system of equations using substitution. So I don't know why I had a problem, but I'm not going to worry about it. We definitely were doing it correctly. We just made an arithmetic error somewhere.
Yep.
Can you graph that ellipse?
Yep. I actually understand ellipses, which is pretty nice.
Cool.
Number 9.
Hold on 1 second. Is this a horizontal ellipse or a vertical ellipse?
Horizontal.
What's that point right there?
That's 0. That's 4, 0.
And what's this point right here?
That would be 0, 3.
They didn't ask for foci, but do you know how to get the foci?
No, he hasn't taught us that.
Well, I'll just give it to you real quick. We won't go through the problem, but that's what the foci is. C. The foci is the distance from the center. The foci is the distance from the center of the ellipse to that focus. And we know A is 4. We know B is 3. So D would end up being the square root of 7. And that's that distance right there, square root of 7. So the point, the focus is square root of 7 comma 0. And that is the key equation, but that only holds true for ellipses, not hyperbolas. With hyperbolas, that is true. So one way to kind of think about it is hyperbolas, it's the Pythagorean theorem. Ellipses, it's not. In other words, ellipses, it's a squared minus b squared. You see why the hyperbola, that's the Pythagorean theorem?
Yes, sir.
C squared equals a squared plus b squared. That's one easy way to remember it. But just remember, that's only true for the hyperbola. For the ellipse, they're subtracted.
Okay.
Okay? All right. What was the next one you wanted to do?
Number 9.
Okay. Let me raise that up a little bit. Okay. So help me label this normal distribution. First of all, what is that point right there?
That's 120.
What percentage of her patients have something greater than 135? Well, she says standard deviation is 10. So that is the mean plus 1 standard deviation, the 130 point.
Yeah.
And I write it like that for a reason, because it's important to know that that's the mean plus 1 standard deviation. And if I go over to 10 more points, that would be the mean plus 2 standard deviations. So let me write that, the mean plus 2 standard deviations. And that point would be 140.
Yeah.
Now, what we need to know is 135 is right there. Everything to the right of that number, the area all to there. Well, what do we know about the area to the right of the mean? It's how much? What percentage of the people have blood pressures greater than 120?
50%.
Okay, so I know it's 50% that way. What I have to do is subtract off this zone. You remember what that zone is?
Which one? The middle one?
This one right here.
34.
Okay. And the next full zone over is 13 and a half.
13 and a half. Do I need to divide that by 2 then?
Yes. So that is 6.75. So what do I have? I have 50% minus these two zones that are not in the solution set. So minus 34 minus 6.75, that's 40.75, 9.25% is the answer. That's how many people would have blood pressures greater than 135. And it's all I needed to know was the mean and the standard deviation. And I think you're beginning to get how this works.
I'm starting to a little bit, yeah.
Let's say we went and checked out a population of old people and saw that 20% of the people have blood pressures greater than 135. Well, what that tells us is our standard deviation isn't 10. It's a bigger number than 10. Because if standard deviation was bigger than 10, then I would have a greater part of the curve to the right of 135. Let's say the standard deviation was 15. Then it would just be 50% minus 34. So we would have 16% of the people with blood pressure greater than 135. So the mean and the standard deviation pretty much tell you everything you need to know about all of the data that's under this curve. And that's because the way they calculate the standard deviation is an extremely complicated method. It's not easy. That's why they always give it to you. They don't give you the data that lets you calculate it. All right. About number 10. You know number 10?
Yes, sir. Those ones are easy.
Good. So we need another page. Let me pull up. We don't have much time.
Yeah.
Maybe we can do.
I have a tutor coming at 8:10, so my mom just said I need to be offline right at 8 o'clock.
You will.
I apologize.
I need to be online with Dylan at 8. So pick a 3-minute problem here.
Pick a 3-minute problem. How about 17A? We can do that one?
Yeah. Well, that's not a 3-minute problem.
longer?
That's all right. We can get started.
All right, let's start on it.
Huh?
Let's start on it.
Okay. We, first of all, what the heck happened here? Any complex number can be written a plus bi. And that can be written as r times the cosine of theta plus I, complex number, sine of theta. And r, here's what you need to memorize. R is the square root of a squared plus b squared, pretty standard. And theta, this is the tough part, theta is the inverse tan of b divided by a if a is positive, and it's equal to the inverse tan of b divided by a plus pi if a is negative. And you don't see this very much. In other words, how often do you have to add something based strictly on whether the denominator is positive or negative?
Yeah.
Hardly ever. So these three things, well, actually, you need the standard form also. That's going to allow us to convert this to polar form quite easily. Okay? So we can actually do this in 1 minute. R is the square root of 49 plus 64. So R is the square root of 113. And the rest of the answer is cosine of whatever that comes out to be. In this case, A is negative. So we need the inverse tan of minus 8 divided by minus 7, and then you're going to add pi to it.
Okay.
Whatever that angle is, it goes there. Not as a theta. Let's pretend that it's pi over 6.
Okay.
In other words, let's pretend that inverse tan of minus 8 over minus 7 plus pi is pi over 6.
Okay.
Here's the answer. In other words, you don't convert it down. Right there is the answer.
Okay. That's looking better.
And if you were to solve this, in other words, if you figured out what the sine of pi over 6 is, you would end up getting right back to this number.
Yeah.
But this is called polar form, where you leave it as the cosine of that angle. You don't figure out what it is and put that number in there.
Okay.
Okay? All right. Justin, I will talk to you next time.
All right. Thank you very much. Appreciate it.
Bye-bye.
Bye.